Okay, in this video, we are going to have a look at PWM on the Raspberry Pi Pico, the RP2040. Now, I'm using the tiny 2040 board, which you can see on my breadboard. It has a smaller footprint than the Pico board, has less GPIO outputs, but it's the same circuitry. And I have a program running, so I can control this LED. I can control the brightness of this LED. Now, the RP2040 has 8 channels of PWM with 2 outputs, an A and a B output for each channel. So we have a total of 16 PWM outputs. And we could feed that to any of the GPIO pins. So I have pin 2 as a PWM output, which is feeding this LED, and I have it mapped to my keyboard. So my 8 key is my up key, and 2 is my down key. So if I go my up key, you can see I'm getting a PWM signal to the LED, increasing it till it's full brightness, and I can take it down with the 2 key all the way down to 0. Okay, to drive heavier loads with PWM, pulse width modulation, like to drive a motor, we would need some type of driver, so we could use a MOSFET, but then we would need a gate driver because of the gate to source capacitance and the gate to drain capacitance, which is the Miller capacitance, and we'll get a Miller plateau effect. So for medium powered devices like this LED on my breadboard, I'm using a bipolar driver, a ULN2803. It has 8 drivers inside the chip, and each one could sink 500 milliamps, and I have them all paralleled, so I could drive multiple LEDs. And they're paralleled, and they do current sharing because the transistors are on the same substrate, so they're matched. And there's a resistive network inside to keep the transistors from going into saturation, so we could clock it at a high speed. So I have it mapped to my keyboard, and so if I increase the PWM, you can see the LED coming on, and I'll take it right up. It's going to get pretty bright. Take it up to the top, and I can take it down all the way down to 0 using PWM. Okay, here's the schematic diagram of the circuit that I built on my breadboard, and it's fairly simple. If you look at the very left, you can see the FTDI module. That's my USB to serial module. The USB connector is connected to my computer running TerraTerm. The TX and RX of the FTDI is connected up to the RX and TX of the tiny 2040. That's my serial port connection. The 3.3 volt output of the FTDI is powering the tiny 2040 through the V-bus pin, and the 2 grounds are connected together. Now GPIO number 2, that's the one we're using, is feeding my single LED, which I shown on the video. It's also driving my ULN2803 driver. There's 8 drivers, and they're all in parallel, so all the inputs are connected together, and all the outputs are connected together. Now this is a current-driven driver, as opposed to a MOSFET, which is voltage-driven, which has a capacitance from the gate to source. There's no capacitance in this driver, so we don't have to worry about that. And this driver now is driving my LED array. So there's 9 LEDs in this array. There's 3 in parallel, and there's with 3 in series. So that's how we drive our LED array using PWM. Okay, here's the code running on the RP2040 microcontroller to set up a PWM channel on GPIO pin 2, and it's written in Mecrisp 4th, and we're going to do some direct register programming, so we'll get into internals of this microcontroller. So there's 5 things we have to do to set up the PWM channel, and here are the 5 things. So when I run the word pwm.init, it's going to run these 5 things, and we'll set up our channel. So the first thing we do, we set up GPIO pin 2 as our output. So we set up pin 2 as a function 4. That's what the first line does. The second line is our divider, our clock divider. So we want a PWM frequency of 1000 Hertz. Now it doesn't divide exactly, so we're going to get 1017 Hertz. So that's what this line does. Third line, we're going to set up the counter compare register. So when it first runs, it's going to be a 50% duty cycle, and that's this value here. Now if we put this value to 0, when it starts up, there'll be no clock running. It'll be at 0 volts, but we're going to set it up for 50%. The next is the TOP. That's the counter is going to count up to 65,534, and then it's going to roll over to 65,535, and then drop down to 0. So that's our top value. We're going to set that up. And then this sets up bit 1 is going to be set in this address, and that's going to enable the PWM channel 1A, and then it's going to start running. So we're going to have a look at the first one. We're going to go through our checklist. We're going to have a look at this line here. So we'll go into the data sheets. Okay, all 30 GPIO pins on the RP2040 can be used for PWM, but we picked GPIO pin 2, which you can see here. So that's going to be PWM Channel 1A. So we're going to remember that. That's the channel we're going to set up. Okay, next, we have to set up the function select. So if we look at this chart, GPIO pin 2, you can see right here, and we go over to PWM 1A, and we can look up, that's function 4. So GPIO pin 2, we have to set up for function 4. Okay, next, we are going to go to the GPIO2 control register and set a base address of 4001-4000 with an offset of 014. So that's our GPIO2 control register. So we'll go there, and if we go to the very bottom, bits 0 to 4 is our function select. So that's where we insert the number 4 to give it a function 4. Okay, I have TerraTerm up and running on my computer, and it's connected to my tiny 2040 board. So I'm going to demonstrate how we could assign function 4 to GPIO pin 2 to make it a PWM output. So we'll have a look at all the functions. So go print functions, and you can see function number 2 is a serial port. That's GPIO pins 0 and 1, and all the rest are 5s. Those are GPIO pins. So GPIO pin 2, right now it's a 5, so we want to make it a 4. So we go pin 2, function 4, then function store. Now if we have a look at the functions again, now pin 2 is function 4. Now it's set up as a PWM output. Okay, here's the formula for producing a PWM frequency of 1000 Hertz. So we plug in 1000 Hertz into the formula, and we'll get a divider. Now the divider is the prescaler divider, and it's in the 8.4 format. So we'll be getting into binary fractions. Okay, next we have to calculate our prescaler divider to give us output of 1000 Hertz for our PWM signal. So we start with the system clock. It's 125 megahertz. That's fed into the prescaler, and the format is 8.4, so it's 8 bits for the whole integer and 4 bits for the fractional. And that's fed into a 16-bit counter with a top value of 65,534. That goes up to the compare counter and output GPIO pin 2, and that's our PWM 1A. Now there's a 1B, but we haven't enabled it. So here's our formula. So fsys divided by fPWM times TOP plus 1 will give us our integer, our whole integer, plus our fractional. So we plug in the values. We have 125 million divided by 1000, that's our frequency of our PWM, times 65,535, that's TOP plus 1. We get a value of 1.9074. So 1 is our whole integer, and the 0.9074 is our fractional. We multiply that by 16 and we get 14.52. If we change that into hex, we get a hex E. So our prescaler value that we're going to plug in is 1E to get a PWM frequency of 1000 Hertz. Okay, the last step, we have to enable the PWM output. So we go to base address 4005-0000, offset A0, which you can see here, and that's our enable. So if we go to there, and if we look down, channel 1, that's our PWM channel, it's bit 1. So if we set bit 1 of this address, it'll enable the PWM output. Okay, so let's have a look at our checklist. So GPIO pin number 2, we set to function 4. That makes it a PWM output. Our divider, we calculated as 1E for 1000 Hertz PWM frequency, but it didn't divide evenly, so we're going to get 1017. We set our counter compare register to 7FFF. That's halfway to TOP, so we're going to get a 50% duty cycle when it fires up. This is where we program our TOP, 65,534, and we store it into that address. And then if we set bit 1 of this address here, it will actually enable PWM channel 1A, and everything will start running. Now after that, all we have to do is type our percentage of PWM. So if we want 10% PWM, we type 10%. If we want 20, we type 20%. If we want 80, we type 80%. And that'll put the appropriate number into the CCR register. That's our counter compare register. And that'll give us our PWM output. Okay, I have a meter which shows PWM percentage hooked up to my circuit. And as I power it up, I'm getting 50%. And if I go to frequency, you can see it's 1017. We wanted 1000, but it didn't divide evenly, so it came out to 1017. So we'll go back to percent. It's 50%. So now with the keyboard, I'll punch in 5%. I'll punch in 20%, 50%, and 80%. So it's pretty accurate. So that's our PWM output. Okay, so that was my little tutorial on PWM using the RP2040 microcontroller. Now it's very similar to other microcontrollers that I've used, and you've probably seen some videos. So dig into the data sheets and look up the PWM chapter, and you can learn more about PWM and how to do direct register programming.